All right, welcome. We are going to be looking at some of the check your understanding questions for the optimization lesson 6 in unit 4 here. So first question, you have 200 feet of fencing to enclose a rectangular field by your house. One side of the field borders a pond and does not require fencing. What is the area of the largest field that you can enclose? Cool. So we have a pond. We'll just draw our pond here. And we're going to try to enclose some sort of rectangular area in fencing. So here we got our whatever, right? And obviously area equals length times width. So we are trying to maximize, because we're going to know the largest field that we can make, our area. So step one, I have an equation. It's not great, but I have an equation. Area equals length times width. Step two, what are my constraints? So I have one constraint here. It is the amount of fencing that I have, right? I only have 200 feet of fencing. So sort of look at this, right? My fencing is going to be made up of 2 widths and 1 length. So 200 equals 2W plus L. This is my constraint. Now, we want to be able to write our area formula in terms of a single variable. Currently, it's in terms of L and W. So we can use this constraint equation to write it only in terms of one of them. So what I'm going to do is I'm going to solve it for L, because that's sort of easiest here. So L would be equal to 200 minus 2W. So we now have figured out a way to make a substitution for L. We can replace L with this. So that's what we're going to do in step 3 of this problem. We're going to replace L with 200 minus 2W. So area equals 200 minus 2W times W. So now we have a nice equation for our area that is only dependent upon the width of this rectangular area that we fill in. Awesome. Last step, and this is sort of the longest here, but we're going to be using our derivatives to find the maximum and minimum, in this case only a maximum, area which we can enclose. So we're going to take the derivative of this. It'll be easiest if I go ahead and multiply this in first. So that's 200W minus 2W squared for area, and then we'll take the derivative of that. A prime equals 200 minus 4W. Cool. To figure out relative extrema, which our maximum would be, we do need to set this equal to 0 to find our critical values. So we add 4 to both sides, 4W to both sides, divide by 4, and we get W equals 50. So this is a potential relative extrema. And it's the only one that we found, right? There aren't any others. So this is probably our maximum value. And so what we need to do here is we need to figure out, if this is a minimum or maximum, right? We can do this in a couple different ways. We can determine whether we are increasing into that and decreasing out, right? Making a maximum by looking at our derivative, picking a number smaller than 50 and bigger than 50 and kind of looking at that. Or we can look at the second derivative, right? So if we look at a double prime right here, and we calculate that, we end up with 0, because that's the derivative of that, minus 4, because derivative of that there. So since we have a negative second derivative everywhere, that's constant, we are looking at a graph that is concave down. So we do have a maximum value, right? Our graph is concave down over the entire function. So really we have a graph that looks like this. So this is definitely our maximum value when the width is 50. Cool. Now, it does ask us to actually figure out what the area was. So when our area is 50, we can go ahead and plug that into this formula here to figure out the actual area. So the area is equal to 200 minus 2 times 50, which is 100, times 50. Okay, that's 100 times 50, so that's going to be 5,000. And our units here are feet, so feet squared. That is our maximum area that can be enclosed. Again, that would incorporate a fence. This is the pond that has a width of 50 and a length of 100. Cool. Again, so that's our maximization process, or our optimization process rather, right? We have to come up with an equation that kind of governs the thing that we want to minimize or maximize, which in this case was area. We need to identify our constraint and come up with an equation for that. Use our constraint to substitute in to our original equation, so that we only have one variable. Then we need to take a look at our first and second derivatives to figure out those minimum and maximum values. Cool. We're going to keep going here. A rectangle has two vertices on the x-axis and two vertices on the curve of 9 minus x squared. Cool. Let's just straight up look at that here. So we have our x-axis and y-axis, and just kind of give it away. This would be at -3 and 3 and 9 up here. And so we would have a parabola that's facing down. And we have a rectangle. So 2 of the vertices are on the parabola, 2 are on the x-axis. So we are trying to look at this rectangle right here. We want to know what the maximum area of that rectangle is, right? So what can we do? Well, turns out we don't necessarily need to look at the entire parabola, right? We can sort of almost look at kind of like half of it and kind of double it, but that's okay. So it's going to occur at some x value and some negative x value, and that these points here would be f of x and f of negative x, right? So we kind of know the vertices in terms of x and the output of our function, and obviously the output of our function is, you know, these things. So the area is going to be represented by this length here, which is 2x, and then the height is going to be represented by, well, f of x. So we have 2x times f of x. And fortunately for us, we know that f of x is 9 minus x squared. Cool. So I've actually done a couple processes here, right? This was my original function, my original area, kind of the area of that rectangle. And then this is sort of my constraint, right? What are the values of f of x? So, and f of x is, you know, based on this particular equation that we have. So kind of by doing that, I have my original equation for area, and then I were able to substitute in my constraint in there to give me a nice equation only involving x's. So now we can figure out that value of x that's going to make this work here. So we'll look at our first derivative. Well, let's not do that yet. Let's actually multiply that out because it'll be a little bit easier to do this. So 2x times 9 is 18x, and 2x times x squared, that'll be negative 2x to the third. Cool. Now we can look at our first derivative. So the derivative of that is going to be 18, and then derivative of this will be negative 6x squared. Cool. So we want to know, when is this equal to 0? What are our critical points? Fortunately, this one's actually pretty easy, right? Add 6 to both sides. We get 18 equals 6x squared. Divide by 6. We're going to kind of carry this forward up here. That is 3 equals x squared. So we can take the square root of both sides. So that means that x is going to be equal to the square root of 3. Or negative square root of 3, whatever, right? So now we know kind of the location of these points. These are at square root of 3 and negative square root of 3. And that these points are at f of the square root of 3 and f of negative square root of 3, right? Cool. So what is the maximum area of this rectangle? Let's use our formula. We got the area equals 2 times the square root of 3 times f of the square root of 3, which is 9 minus the square root of 3 squared. That's 9 minus 3, that's 6. So we have 2 square root 3 times 6. So we get an area of 12 square root 3 as our maximum. Cool. Now, I presumed that this was the maximum, right? I could confirm that, right? Let me just kind of confirm that that actually was a maximum value. And so again, a handy way of doing that is by taking a look at our second derivative. So let me see if I can kind of scroll down just a little bit there. So our second derivative would be equal to, that would be 0, so negative 12x. And we want to know at the square root of 3 whether this would be concave up or concave down. So if I plug in square root of 3, this is a negative value, right? That indicates we have concave down at this point. So this is a maximum, right? If this was a positive 12 square root of 3, right, that would indicate concave up, would indicate a minimum. So again, using that second derivative to determine concave up or concave down or concave up is very helpful, right? Concave down means we have a maximum value. Concave up means we do have a minimum value. All righty. So I'll just go ahead and do one more of these for today. So a sheet of cardboard with a side length of 60 inches is folded into a rectangular box with a lid. 4 squares with a side length of X and 2 rectangular sections are discarded in order to show to fold the box as shown. For what value of X is the volume of the box maximized? Cool. So again, these are our squares of side length X that we're cutting out. This cardboard piece here, right, is 60 by 60 after we've kind of cut out some of these things. And we want to know what value of X gives us the biggest box. Cool. So let's kind of think about an equation here, right? Already kind of sneakily given to us. So we have a volume equation of V equals length times width times height. Don't love any of that, right? Because we have X's, and none of these are really X's, but let's just sort of think about it. In terms of our box, right, the base of our box, that's going to be a length times a width. And the height of the box, well, that when we fold up like this flap here and this flap here, that's going to be the height of the box. So it turns out height is just X. So that's good. That gets X involved in there somewhere. Now, let's think about L in terms of X. So we know that this total side length here is 60, and that these two parts are X and X. So this length of our box is going to be 60 minus 2X. So that's 60 minus 2X. And the width of our box, this one's a little bit trickier, right? Our width of our box, well, if I kind of look at this line right here, these two widths and these two X's have to add together to be 60, right? So I kind of have a little bit of an equation in that sense. It's 60 equals 2X plus 2W. I can divide everything here by 2, right? So I get 30 equals X plus W. And then to solve for W, right, it's 30 minus X equals W. Cool. So I was able to sort of do that. So W equals 30 minus X. So now I have, these are all of my constraints that I'm working with, right? My big constraint here is that my box is 60 by 60, or my cardboard is 60 by 60, and I was able to use that constraint to make substitutions for length, width, and height, giving us a formula that only has X's. Right? We would like to go ahead and multiply that all out. I'm going to go ahead and do that, but I'm gonna do it on Mathway here real quick because I don't feel like kind of doing all the calculations, but hopefully we can do that. All right, so when I multiply that out, I would really like to have it in this form, so I'm doing it this way. I get 2x cubed minus 120x squared plus 1800x. Cool. So that is my volume formula. So we want to figure out a maximum volume. So we're going to analyze our first and second derivatives. So this was sort of step two. Step two, making the substitution. Step three, subbing it in. Step four, derivative, v prime. So we get 6x squared minus 240x plus 1800. So we want to know, when is that equal to 0? When is that equal to 0? Lots of options here. Everything here is divisible by 6. We could kind of reduce this down. 240 divided by 6 is 40 x, and then 1800 divided by x is going to be 300. This is probably factorable. Two numbers that multiply to 300 and add to negative 40, potentially. Do I want to do that? Probably not. Well, yeah, I mean, okay, multiply to 330. 300 is 30 times 10. Yeah, and so that works. So this is x minus 30 times x minus 10. And by solving that, we figure out that x being 30 and x being 10 are our critical values, right? But which one's a maximum, which one's a minimum, which one's maybe not possible, right? Turns out a 30 centimeter cut, right? That's actually not possible, because, you know, this whole thing is only 60. If we do a 30, 30, 30, right? We've cut off this whole part, this whole part, this whole part, and this whole part. We have nothing left, right? So we can't actually do 30s, or perhaps better thought of, this would, you know, be a minimum value, not a maximum value. So the one that's potential here is 10. So let's figure out if that's a maximum or a minimum volume by taking a look at the second derivative. So our second derivative would be 12x minus 240. And we want to know, if I plug 10 into here, what do I get? Well, let's do that. 12 times 10 is 120 minus 240. That's negative 120. So what does this tell me? Because I have a negative second derivative, that means my graph is concave down there. So this is a maximum. This is going to give me a maximum value for my volume function because of having a concave down value here, a negative value. So to answer this question in final, we want to figure out what is the maximum volume. So I'll go ahead and plug that into here, x being 10. So that would be 60 minus 20, so that'd be 40. 30 minus 10, that'd be 20, and then times 10. So that's 8,000 inches cubed. That is our maximum volume when we make cutouts 10 by 10 inches. Cool. I'm going to go ahead and stop there. Hopefully that was helpful. Go ahead and try some more of those optimization problems, and I'll see you all next time.